want to do is actually to have a base doped higher with respect to collector, because then there won't be such a large variation with voltage on the base side of the space charge region. It will more extend on the collector side. With some backgrounds of the PN junction, we're going to move to bipolar transistor, which is a bit more complex because we have two PN junction. We're not going to discuss all the same details, but having learned some topics that let us understand what happens on the PN junction and forward and reverse bias, we're going to take this information to bipolar transistor to understand better the operation and where certain phenomena come from. So for certainly transistor, which is bipolar transistor, we cannot take simply these two discrete diodes, because we really rely on the thin region of the base in order to have efficient transistor. So we can have either NPN which will work with forward bias base emitter and negative reverse bias base emitter. What we want to achieve is to accelerate in the forward biased junction where the currents flow and produce charge carriers. We want to actually accelerate them across the collector applied electric field to produce collector currents and avoid recombination in the base. So the other type of bipolar transistor is PNP, where it's the opposite situation. So we still have the forward bias base emitter junction and applied higher voltage across emitter collector in order to accelerate charge carriers to pass over the base into the collector. And I chose this slide because this type device to illustrate what happens, because very often in the books we start first with N-channel transistors or NPN, and the complementary side you have to work out for yourself. So here, let's start backwards with PNP transistor. So for the forward biasing the emitter-base junction, we have to apply more positive on the P side and more negative potential on the N side. So like that, we have the charge carrier. So the most interesting charge carriers interesting for us are the holes traveling into the base region. And then in the base region, we have a collector which is biased more negative with respect to the base. So it's this junction is reverse biased. And here we have the space charge region. So as soon as the hole which has enough energy to reach the space charge region, as soon as it's in the space charge region, it will see the electric field of the ionized ions on the N side and continuously on the P side, and it will be swept into the electric field attracted to the collector side. And this produces the collector current. If we are unlucky and the base region is very wide, then charge carriers, shall it be here for holes, or in this case for electrons, the charge carriers are going to recombine. Therefore, we would like to choose such doping parameters and geometry of the device that this recombination is unlikely, so that the base current is low, possibly low, and collector current is possibly high. Like that, we ensure that we have high beta, high current gain of the transistor. So the expression of the collector current is the IS, saturation current, times the exponent with Q over KT, times the base emitter voltage. So it's very similar to the equation of diodes for large enough base emitter voltages, so that this exponent is higher than 1. And this saturation current is explained with this formula, so we can see what is dependent of. It's basically dependent on this technology parameters. For sure, temperature, because we have the diffusion constant. The area of the diode, because the wider it is, the bigger current. But above all, also base region doping concentration and the width, the geometrical width of the base region. And yeah, that's it. So then we have if collector emitter voltage is greater than base emitter, then we have this nice relationship that the collector current is equal to beta, the current gain, times base current. And in order to have a good amplification, what was already said, first thing, the base region has to be very thin. Actually, here it's written as the second. And secondly, emitter doping level should be much higher than the base doping level, than the acceptor level. So the doping in this region compared to this region. So we would like to have a lower probability for recombination, small space charge region on the base side, so more extending to the emitter than to the base. And therefore, we have a higher doping on the base, on the emitter than on the base. For the transfer characteristic, we have the base emitter voltage as a function of the collector current. So that's how we draw the transfer characteristics. And here we can define, so take the expression that we have already seen, but now actually plotting as a function of this base emitter forward voltage. What we can define here is the transconductance. That will be very interesting if we want to amplify the collector current modulated with the base emitter voltage, for example. More often, and of course, it's the expressions are valid when the collector emitter is much higher than base emitter, because then the charge carriers can easier reach the collector and take part in the collector, into the collector current. So then this already known characteristic. The other format and other information that we learn from characteristics is, because it's three-terminal device, we can plot lots of things, and this is the other customary plots that we see, the collector current as a function of collector emitter. And in this plot, we can characterize two regions. One is the saturation region, which happens at the lower collector emitter currents, and active region that happens at the large collector emitter current. So ideally, we would like that it's a flat characteristic as a function of the collector emitter current. We see some sloping, and depending on what type of device we take in the catalog, for example, of the bipolar transistors, this slope might be different, and it's defined by this early voltage where all the characteristics, if extending into linear, they meet in one point. So as a collector emitter decreases, it is lower than base emitter voltage, then the collector current starts decreasing, because we start having we had first one forward biased, one reverse biased junction, and then the collector base junction goes out of the reverse bias. So then, in that case, the current gain is decreasing, because it's not any more effective device, and effectively we can tell that the beta coefficient is decreasing. And we are going to be talking also about about MOSFET transistor. And for MOSFET transistor, we also have something called saturation region, but it's totally different meaning of the saturation. So here I would like already to make an attention. The saturation region on bipolar transistor characteristic is different interpretation from the saturation region of the MOS transistor, where we're talking about current saturation. And also the characteristics here is collector current as a function of collector emitter voltage. In the MOSFET transistor, we have different naming of the terminals, and it's just not to be confused. So similar thing, as we decrease the collector emitter voltage is what I would like to illustrate here. So the most left plot is with the higher collector emitter voltage, and the most right one is the lowest. So what happens, what the difference is that the space charge region is decreasing because we have less and less reverse bias junction between base and collector. And because of that, if the charge carriers that were supposed to be accelerated into the collector, they are crossing towards the edge of the base collector, those electrons, we would like that they go into the electron collector region. But because the space charge region is lower, there is lower electric field, this acceleration is smaller, and we have higher probability that actually those charge carriers recombine. And in addition, at some point, we are going to have also the electrons, once this junction is forward biased, then also the electrons come towards the base, and the beta effectively is decreasing. The other region, the active region, what I would like to explain at this point with respect to the p-n junction of space charge region effects is the early effect and where it comes from. So the normal characteristics where we neglect the early effect can be described by the without the expression in the brackets at the end. If we include the fact that there is early effect, so the characteristics are not flat, but we see this sloping, so a finite early voltage, then we multiply the current by this expression in the brackets, and that's what's modeling these characteristics. If we look at the cross-section of the bipolar transistor, here we have again NPN. We have this collector emitter collector base junction, which is reverse biased, which produces certain space charge region. And now you remember that as we increase the collector emitter voltage, then the current was increasing. And where does it come from? So we have the space charge region that, because we have at the same time larger bias applied in this reverse bias diode, the space charge region is increasing. So the base region becomes even thinner, because much of the base region where potentially the electrons might recombine. So they won't recombine so easily because there is less base. They cross to collector side, and then they are swept into this collector. So effectively, with the lower probability of recombination because thinner base region, we have effective increase of the beta, and which is dependent on the applied voltage. That's why we model in that way. And one of the final things regarding, relating the doping level of the different regions of the bipolar transistor and the performance, I would like to summarize with this table. So we have those three regions: emitter, base, and collector. And we have three parameters that we might consider important. Depending on the applications, we might want this or this parameter to be more important and go in certain direction. But very often we want the three parameters are current gain, early effect, and leakage current. Very often we want the current gain to be large. What do we have to do for that? So the important properties is to bias, dope the doping level of the base to be low and high for the emitter. So like that. there is less probability of recombination in the base region. If we care about early effect, to have more voltage stable behavior of the device, then what we want to do is actually to have a base doped higher with respect to collector, because then there won't be such a large variation with voltage on the base side of the space charge region. It will more extend on the collector side. So that's if that's what we would want to have in the device, that's what the doping balance has to be. And finally, for the leakage current mainly comes from the junction of the base and collector, because the collector current is what we are then. It depends, of course. It could be that we care also about the leakage current of the emitter base. So, in any case, if we want to have lower leakage current, whether it's base emitter or base collector, we want both sides to be of higher doping, so that the space charge region is possibly low, and then the volume where the thermal generation of charge carriers that contributes to this leakage current is as small as possible. And I'm referring to sometimes what I was all that I was talking now about. I was referring to data sheets, thinking a little bit of the bipolar transistors that we have available as standard components. But there are also very important components in the integrated CMOS technologies. And here are some examples where we might want to use them. So then we have actually special processes called BiCMOS, which combine the field effects transistors in the same process as bipolar transistors. So, for example, for high-speed amplifiers, or as input stage in some application, because there will be low voltage noise of the bipolar transistor, on the contrast to MOSFET transistor. For high output power, they can be used as drivers and as over voltage protection on the I/O pins of the circuit that we have to place in the package, and then for handling, for safety against also ESD, electrostatic discharge. These silicon-controlled rectifiers are based on bipolar effects. And because I'm talking about these protection devices, I would like to also show some an effect called latchup that happens in the MOSFET CMOS technologies, where we have a complementary PMOS and NMOS transistor. We will be talking about it in the next part, about the operation of these devices. But already here, because we have this parasitic bipolar, I think it makes sense to point out here. This is the cross-section where we have p-channel transistor, n-channel transistor, field effect, both cases, and they coexist in the same structure. And if we look at the cross-section, we will see these doping regions of different type, and why we need all that we will be still discussing in the coming lectures. But basically, we end up having n-p n structure, so n source, p substrate, and n well, and p and p, because there is p-type substrate on the other side. So basically, we have coexisting structure of two bipolar transistors. And what can happen is that one junction, because of over voltage spikes at the power supplies, lower or upper power supply, or maybe ionizing particle, this happens in the normal operation. So where we have high power supply, ground, both applied, and then these transistors, which should be normally off, suddenly the base emitter of the NPN transistor gets forward biased. So that means we have current through some maybe very small current because of the series voltage drop across this resistance. And then some collector current starts flowing. It would maybe be just transient effect and disappear. But if we have enough bad luck, then because of the parasitic resistance, so both resistances are parasitic related to low doping of the semiconductor, but important enough that it could cause forward bias of the base emitter of this transistor, which then results in the collector current through here, which in effect sustains the base emitter voltage of the NPN. And in the end, what can happen is that we will have an open pass through both transistors from upper supply to ground, something that normally should be just some leakage current, something negligible. So this can happen when the beta of these parasitic transistors are large enough that this positive goes in positive feedback, and the collector current sustain the forward bias of the opposite polarity transistor. So if that happens, it can lead to thermal damage. And to minimize the risk of latchup, we have to make proper dimensioning, make the bipolar transistors actually in this case as inefficient as possible. So base region effectively very large, and the doping levels we cannot choose in the CMOS technology, but maybe some other precautions in terms of layout, how we place the components to make it inefficient and this latchup not to happen. With that, we have covered the important topics of bipolar transistors that might be related also to integrated technologies, on which we will be focusing for most part of this lecture. And if there are any questions, we still have a few minutes to discuss. Otherwise, thank you, and we see us next week on Friday.
You're the signal in my static hum, a perfect match we've overcome. Wires crossed, but we still